Hello and welcome to the second part of the first lecture. So this is lecture 1, part 2. We're going to continue discussing elasticity of materials. We looked last time at elasticity, introduced Young's modulus and stress and strain for objects under tension. We applied Hooke's law, which we all are familiar with from springs, but we applied it to other materials as well. So we'll jump on over to the slideshow and we'll pick up where we left off. It's just showing you it's the same lecture. We are going to 28, pushing or pulling. So last time we talked about Hooke's law for pulling on an object. The example we used was hanging a sculpture from a thin rod from the ceiling. So that rod was going to be under tension. It was being extended, that's tension. But of course, things aren't always just under tension. So this step now is to think about the opposite. What happens when we are pushing on an object instead of pulling on it? So we move from tension to being compression if we are pushing. So when we had tensile stress, tensile strength, tensile deformation, we're going to have compressive instead, compressive stress, strength, and deformation. We're also going to introduce shearing. That's easiest to explain when we have a diagram, so I'll leave that till we get to that slide. So the equations that we saw for tension are exactly the same for compression. So we still have force is equal to K delta L. K is still our Hooke's law, spring constant. We have the same formulas for stress, which is like pressure, force over area, and strain, which is the fractional change in length, delta L over L naught. And we've still got the ratio of the relationship of those two, stress and strain, given by the Young's modulus. And it's still going to be the same equations. So everything we've done for tension, we can just carry straight over to compression. As I've noted down the bottom there, the forces are going to be pointing in the opposite direction to the tension forces, because obviously now we're pushing inwards on the object rather than pulling outwards on it. The Young's modulus may be different, although they're usually the same, but it is worth just double checking if you ever do any research or reference anything. Just double check if the Young's modulus does vary for compression versus tension. And also you'll sometimes see negative signs brought into it. We already said the forces were going to be in the opposite direction from the tensile forces. So sometimes we use negative signs to represent that, but as long as we're clear, as long as we understand the system, we don't always need to put those negative signs in there, because we know which way the forces are going to be going just by stating whether it's under tension or compression. Shearing forces are, as I said, easiest to understand when there's a diagram. So imagine this is a box. It could be any kind of block of metal or something, but if it's a cardboard box, the results would be a lot clearer. If you have this box and you push on one edge, the top edge on one side in one direction, but hold the bottom edge in place on the other side, then the box would start to slant, it would start to shear. That's what shearing means, that sort of tilting over of this shape. Right, so it's skewing the box or cube or block or whatever you've got. So the stages are the same as we saw for the other deformations: linear, elastic, plastic, and then failure. Same thing's going to happen. But now we're getting this deformation in a very different sense. It's not just changing one of those lengths of the object, it's actually changing the shape, the angles involved in that shape. It's changing the structure itself. So for shearing, we do have to make some slight adjustments to the calculations, not in terms of the terms and the formulas we use, but just in terms of what they apply to. Now that might actually end up being more confusing, but that is the way the terminology has ended up being used. So we still use the same terms. We still use area, change in length, and original length L naught, but now they apply to very different things. So I've done a diagram on this slide, which is the easiest way for me to show that to you. If you've got a force pointing, two forces pointing in opposite directions, one on the top to the right in this diagram, one on the bottom to the left, the area that we're talking about for our, remember the stress is a force over an area. The area for that is going to be the area on the top, the one that's in line with the forces. Right, so that's the area that we need to use. The length that we care about, the L naught, the original length, is actually the one perpendicular to the forces. So in this case, the height of that block. And the change in length is essentially how much it tilts over. So from where the block started, how far does that point move across? You see I've drawn that, I've illustrated that on the right-hand side here, but it's actually the exact same, sorry about that, the exact same length here as if you did it over this side, right? All we care about is how far from that point to that point we've moved. Assuming we only have shearing, those two would be the same. If we had compression or tension at the same time, then it would get more complicated. At this stage, we will only deal with one at a time, but do be aware if you see other problems that those two measurements could potentially be different. The left end and the right end could be different if you had tension or compression at the same time. As I said though, you don't need to worry about that right now. So for shearing, we can't use the Young's modulus, because the Young's modulus was to do with the compression and tension, so the force and the deformation all being in line. But shearing now, we're moving into this other realm. We're moving to forces being perpendicular to deformations and other things going on. So we need a new term, and to be unimaginative, we've called it the shear modulus, and we use the big G for that, big letter G. But the equation is still, as I said, still the same. We've just got new terms that mean new things. So we still have stress is equal to modulus times strain, but now we're using the shear modulus, not the Young's modulus. Other than that, everything's the same, provided we use those new definitions for area length and original length, or change in length and original length. The other thing that we'll mention as well is volumetric compression. So when we talked about tension and compression so far, we've been talking about tension and compression in one dimension. So just stretching or squishing that object in one dimension. But we can have volumetric compression. For example, putting something underwater, water pushes on that object from all sides at once. So if there was enough pressure from the water, the object might get smaller, but that would be all around in all dimensions that it would get smaller, not just in one dimension, like when we hang something or stack things up, right? That's only in one dimension. So if the object is made of something with any compressibility, which as it sounds like, it's the ability to be compressed, then the volume would decrease as you increase that pressure. So as I said, putting it underwater or even having it in a high pressure environment, if you've got such a setup in a lab somewhere, you can increase the air pressure and watch the volumetric compression. So that's the whole thing, as I said, all three dimensions decreasing. The bulk stress and bulk strain are the terms we use when we're discussing volume changes. So we had stress and we had strain, but again, those were all one-dimensional terms. So we bring in this new term, bulk stress and bulk strain. If we submit an object to a change in pressure, then it's a bulk stress. The stress is acting on all directions at once. As I said, all three dimensions, not just one of them, and any resulting volume change is a bulk strain. So just like we saw with strain originally, which was a change in length over length, the fractional change in length, here we have the fractional change in volume, delta V over V naught. And again, we still have the relationship by a modulus. This time it's the bulk modulus. As you might have been able to guess, we've been using the word bulk a bit. So we've got bulk stress and bulk strain, and so we're going to have bulk modulus. So the bulk stress, which is delta P, you'll notice we've switched to calling it pressure here, whereas stress we saw was the same thing as pressure, but it was, again, one-dimensional. We're talking about the stress along one dimension of this object, perpendicular to the force, the cross-sectional area perpendicular to the force, and the stress that it experienced along that. Now that we're dealing with a volume, pressure is perfectly sensible. It makes perfect sense to talk about the pressure that an object is experiencing. So we've gone back to using P for pressure, the bulk modulus B, and as we said, the bulk strain, delta V over V naught. So that's, again, same equation, but now with new terminology just to reflect the fact that we've moved to a three-dimensional consideration in the volumetric compression. So here's some examples of moduli. So this is the same table we had earlier, earlier we only looked at the Young's modulus, but now we've got shear modulus and bulk modulus to consider. We understand what they are now, so we can actually look at the numbers and just have a see how they relate. So steel for Young's modulus was 200 times 10 to the 9 newtons per square meter. You can see that for the shear modulus, it's only 80 times 10 to the 9, and the bulk modulus is 140 times 10 to the 9. So the Young's modulus, remember, was just a single dimension. The bulk modulus is all three of them at once, and the shear is essentially how much it'll skew or tilt over. So as you can see, they are different for all of the objects, which makes sense because it's a very different sort of deformation. So the properties aren't going to be exactly the same. Those give an example of the different values. Take your time to look through that. You will always, of course, be given the values we expect you to use. And speaking of using some values, we'll do an example. We've got a shearing force. So here's a specialized piece of factory equipment. A cube of cast iron is being subjected to a shearing force of 4.7 times 10 to the 6 newtons. The cube measures 92 centimeters in each dimension. How far in the direction of the shearing force does the top of the cube move relative to the bottom? So if you want to pause the video and have a go at this, now that you have seen how the equations all work, we are using the same equations, but now we're obviously going to be using the ones for shearing rather than tensile deformation. You are free to obviously pause the video and have a go at it. I will continue on right now. I will jump over to the document camera and we will have a go at this problem. So first things first is writing out what we know. We know that we have a shearing force of 4.7 times 10 to the 6 newtons on our piece of factory equipment. We have dimensions 92 centimeters. So we've got a cube, and every one of these is 92 centimeters. And of course, we want to know the height if we're applying a force in this direction. So if we're applying a force here and here, we want to know this height. But of course, because it's a cube, L naught is going to be the same regardless of whether you get it right or not. L naught is going to be 92 centimeters or 0.92 meters. And we've been told that it's cast iron. So you'd have to look back at your table of data and you would see that cast iron has a shear modulus G of 40 times 10 to the 9 newtons per square meter. So if we've got all of that information there, there's one other thing we need to know, but that is just calculated based off this, and that is the area. So remember that what we're looking for is the area that is parallel in line with those forces. So it's that one I've just shaded in green. And of course, that is just going to be L naught squared because we have a cube. So it's nice and simple to calculate that. L naught squared will give us the area. So that tells us the information we have. And of course, the thing that we're looking for is delta L, right? What is the amount that this tilts over? So remember that as this pushes here and this pushes here, this is essentially going to tilt over and we'll end up with this shape, something like that. And we're looking for this distance here, delta L. Hopefully that shows through right on the video. That's the value we're looking for. So we have to figure out how we're going to get to delta L from this information that we have. And as I said, we have the same formulas. We're still using all the same formulas as we used when we looked at tension, at the elasticity under tension. So we know we're looking for delta L. We could start by looking at which formula has delta L in it. And of course, that's going to be the strain. We get the strain is the fractional change in length. So if we rearrange that because we're looking for delta L, that gives us delta L equals epsilon, or the strain, times L naught. So that is the formula we need to put values into. We need delta L, we want delta L, so we need L naught and epsilon. We know L naught already, so that's fine, we can leave that, but we have to figure out what we're doing for epsilon. So epsilon, remember the strain is going to be from our stress and strain relationship that brings in the shear modulus. So the stress is equal to the shear modulus times the strain, which means that we're looking for epsilon, remember, because we want to put that into this equation. So we're going to get that our strain is equal to the stress over G. And now we can put that into this equation here. So put this into here, we get delta L is equal to the stress times the original length over the shear modulus. So now we're getting pretty close because we know G, we know L naught. We just need to figure out what our stress is. And hopefully you can all remember that stress is just force over area. And remember we had our force. We know the area is just L naught squared. So we actually know both of these. And that means that we can put this in place of our stress in this formula. And it becomes force over area times L naught over G. And now you can put in all your values, or if you realize A is L naught squared, so if we change that to L naught squared, then you'll realize that this actually cancels with one of the L naughts on the bottom, and you get F over L naught G. So now you've got F over L naught G. You can put in your values for those. Now, some of you may have attempted or have been tempted to, if you did it on your own or were thinking about how you would approach it, you may be tempted to actually calculate this at this point, 92 squared, and get out a value, which is going to be 0.8464, I believe, meters squared. And then you'd put that into this before you replace the A with the L naught. That's fine if you want to do that. Obviously, you're bringing in an extra calculation, which brings in possibility for errors or rounding or mistakes even. So if you are comfortable doing the rearranging of mathematical formulas, doing that algebra, this is, in a sense, it's the safest way to do it because you're doing the fewest calculations. If we plug in those numbers, then we find out that we get 1.2772 times 10 to the negative 4 meters as our change in length, which you would present as 1.3 times 10 to the negative 4, given everything was given to 2SF. So you could present that way. You could also change it into millimeters, just to get more of a feel for the amount of shearing. And that is 0.133 millimeters. Remember, a millimeter is 10 to the negative 3. So that would give you 0.13 of a millimeter, slightly more than a tenth of a millimeter is how much it would skew. Now, this was a block of cast iron that was almost a meter, 92 centimeters in every dimension, and it was experiencing 4.7 times 10 to the 6 newtons of shearing force. 4.7 meganewtons of shearing force, and it only deformed by a little over a tenth of a millimeter. So again, these sorts of values that we're dealing with often aren't very large when we've got these smaller objects, but as you scale up, because those original lengths are increasing, you're going to see bigger deformations. So as you move into the realm of civil engineering, into buildings and bridges and other things, then these can become very noticeable and very important values. The maths, of course, all remains the same. The equations are still the same. Back to our slideshow now. As you'll see when you look at the slides, the solutions are given on the slides, so you can follow along there. Obviously, I've done it by hand, so you can get a feel for the working. So we had failure when we talked about tensile strain and stress, and if the stress got too high, we got failure. So when that happens, we also call it fracturing, right? And it happens at different points for the different types of stress. So you remember on that graph that we saw, at some point you reach the maximum force, and after that, any more force being applied will result in the object breaking. That maximum force is different for each different type of stress we've talked about. and that is called the ultimate strength. Sorry, the maximum stress is called the ultimate strength. Obviously, the force will depend on the actual properties of the object, whereas the stress, the maximum stress is that force over the area. So the maximum stress is called the ultimate strength of the object, and we've got some examples of that here. Again, you'll see that they are not always the same. Tensile and compressive often are, not always, but often are. You'll see immediately cast iron, they are different for tensile and compressive, but for steel, the tensile and compressive are the same as for brass and aluminium. So those are often the same, not always, so you do have to check. And then shear strength is almost always different. Aluminium, might notice, is actually the same for all three, but it's more commonly different for the shear stress. So again, you'll look up the values and you can use those same formulas that we just played with to figure out the ultimate strengths. This idea of ultimate strength, when combined with static equilibrium, will tell you when a structure might break. And more importantly, overall, all the ideas we've talked about, the stress and strain for the different types, tensile, compressive, and shearing stresses, they will all be able to be used to analyze structures. So bridges, buildings, all sorts of things, anything that you're going to construct that is going to be experiencing some kind of stress and strain just because of the weight of itself, because it's got to support itself. And in the case of buildings, it's got to support people. In bridges, it's got to support vehicles and so on. There are going to be a lot of stresses and strains on all of these, and more importantly, they can often be changing. These stresses and strains can change as people and cars and things move around. So you have to be able to understand all of those forces, calculate all of the different angles, not you personally, but the people designing them have to be able to. So the concept of static equilibrium is that hopefully the structure will stay at rest when you put it there, right? That's our goal. We build a bridge, we want it to stay where it is. Then we have to use all the concepts we've discussed here, all this compression and tension and shearing, and figure out all of these for all of the components and make sure that no single component will fail, because obviously if a single component fails, then that will follow on to other components failing and so on. So you've got to check every single possible component of that structure and make sure that every single one is well within its limits for deformation. So we won't go into any more detail on that, but this was just to show you that it does have very practical applications, very important practical applications. So that's the end of the theory content for this topic, for this lecture. The summary on this slide just lists all of the things we do. I'm not going to read right through that, but it's just a recap, a chance for you to have a look, make sure that you've registered everything that we've talked about. I always end my lectures with a few problems. If you ever have me in a physical classroom, I will always fill up any time that we have left at the end of the lecture with a couple of problems. For now, I'm going to do those in a separate video so that if you want to come back and just watch the practice problems from the lecture, they'll be in a separate video and easy to find. So I'm going to call it the end of the lecture here, and I will see you at the next one where we do a couple of practice problems.